Okay, so today we are going to introduce our new Visual Nand Reconstructor 6.1 update, which was released some time ago. And firstly, I would like to say that today we will have two parts of our presentation. Some theory and then some practice, where I will show you our new functions in action and explain some things using real cases and real data. So let's start. And of course, we will start from presentation of our new resources. Here you can see the list of new ECC code words, which are now automatically detected, new scramblers, and new configurations for Nand chips. Of course, you can find all of these elements in our database now. I think that's a clear thing for every one of you, and there is no sense to stop at this slide. So let's move on to our new pinouts that are also added to our pinout database. And now you can also solder such chips on your monolith boards and successfully read them by our beautiful software. And one of the most revolutionary things we have introduced in this update are SLC protocols for SanDisk, Samsung, and Hynix Micron chips, which now allows you to work with chips that were writing data in SLC mode. And of course, I will also show you today an example of such case when we will talk about FC controllers on practice. Okay. And there is a visual example of how such new protocols for pseudo-slc areas of Nand can be now used. And you can clearly see that for now, SLC blocks are read more clearly, and ECC looks much more better than in the case we were reading such chips in standard mode. And at the moment, we can even correct such blocks without making reread procedure. Okay, and the next thing we would like to introduce to you is some settings in reader. Now it's possible to perform reset of the reader without reconnecting it physically. In case of glitch, you can just press reset reader on the top of toolbar or restart the software. I think this feature is very useful because, for example, I was working with some cases that were using too much RAM memory on computer, and unfortunately, some of such cases were crashing. And then I just rerun my software, and I had a reader active on workspace still, so there was no need to reconnect it manually, especially if you're working remotely with your computer. In such times, I think it's very useful feature. Okay. We have also introduced some new AI-based elements, such as FC XOR key generator, which is related to devices that used FC controllers. And to be honest, last time we had many cases with this controller, and I think it's a great introduction in our software. But of course, that's not the only thing we would like to introduce to you today related to FC controllers. Of course, we will talk also about bad beats. Okay. We have also added a feature related to AlcorMicro, ITE, and old Phison controllers, which is also XOR key synthesis generator. I will also show you today how it works. It's a very, I think, great feature because I had some cases last time when there was not an XOR key in our database, and our generator was able to make it by itself. So the clearance of this element is very high. Okay, so let's move on. And of course, we have added also to user version improved CBM XOR generator, because as you know, in the previous update, it was only in test mode, but after some test period, we have introduced also for our clients, and you are now also able to work with it by yourself. The CBM XOR must be used after normal XOR key element with a static CBM XOR key. We have shown this feature in a previous webinar, so you can just click here. Yes, that's a feature I have done for our YouTube, because this webinar is also recorded, as you know, and you will also be able to find it on our YouTube channel, where you can also listen about CBM XOR, which was introduced, as I told, in the previous update. But it's now available also for you, so you can use it. Okay, and the main thing, the main feature of this update, I think, is bad beat column remover. As you all know, we had a deal for some time with bad bytes columns, especially in AlcorMicro or Silicon Motion controllers. But some time ago, we met some cases with mainly first chip controllers where there was only bits excluded from usage in the dump. So we have worked for some time on this bad bit column remover, and now it's finally available also in user version, and it's quite intuitive element. And of course, I will also show you today in practice how it works and what are main questions on this element and how they can be solved. What are the problems? What are the main problems which we can meet in such cases? Here, it is clearly seen that bad bytes columns are in the dump, and you can see that they can get a different shape. They can be like FFs or something like you can see in the left part of your screen. But we are not talking today about our bad column remover, but just bad bit column remover. But of course, if you are interested in the theory about bad columns, what it actually is, you can also move to our YouTube channel and watch a video about bad columns. It's also available. Okay. Now let's move to the bad bits. The thing is, the main difference between bad bits and bad bytes is seen even in the name of these problems. Let's say that on bad bits we are operating bits, and bad bytes columns we are operating bytes. So have a look here at those pictures. You can see that not the whole byte is excluded from usage by controller, but some bits. Okay, and here is a theoretical part of our today's webinar, the main part, I think, because why does bad bit, why can bad bit affect the data clearance, and how we can fix that problem? You can see that if we have bad bit in our page, in our data, we are reading the hex value equal to 12. And if we exclude this bad bit, it's a different story altogether, because we are reading byte in hex as a 4, because the values are different in this byte. And that caused a problem when we were working with chips that were operated by FC controllers. Okay, but that's not the whole problem, because when we were working with bad bytes, we were just excluding them from usage, and then just writing additional FF bytes to the end of the page. With bad bits, it's quite more complicated problem, because controller was working in such way that he was adding bad bits to the data, to the page, and then he was writing additional bits to the end of each code word, which contained bad bits, to make the start of the next code word proper, start it from the byte that was defined as a standard. You can see it here. In this case, we had 3 bad bits in our code word, so the controller was able to write additional 5 bits to make the whole byte full, to make the start of the next code word from the proper place. Okay, so I will also talk about this problem more, not more, but just deeper, while we will be talking about this on practice, because I know that theory is quite a complicated one, but when we will have a look on a case, there will be possibility to see it by yourself, and I think it will be much more clear. Okay. When bad bits are marked and removed, the rest of the page is moved to the left, and such removals can also make a problem while we will try to define a page structure and then extract data. So when we have 3 bad bits removed, the rest of the page gets shifted also 3 bits to the left, exactly how it was in the case of byte columns. So, but I think that at the practice case, it will be more clear. Of course, we must also exclude the additional bad bits that controller also had written to the end of the code word, and we will do it just with our element 2, because we will still work with bad bits. The main thing that in such cases you will need to define a page structure before bad bit removal, but I think for advanced users like every one of us, that's not the big problem. So to conclude the bad bit theme, I would like to say that the whole process of bad bit removal contains 2 steps: removing of standard bad bits from the data chunks, and then bad bits removal from the end of the code word to make all our code words within the page similar. Okay, so let's move to the practice. Today there will be also 2 cases shown for you. One related to AlcorMicro XOR key generator, and one related to the FC bad bits removal, and also FC XOR key generator 2. So I will now okay. And now I will show you the AlcorMicro XOR key generated in action. And I would like to say also that while the XOR key will be generated, you will be able to ask your questions if you have ones. Because, as you know, it will take some time, but we are working all the time to improve the algos of our software, of such generators to work faster. And as you can see, in this case, I have extracted some blocks with data. I will show you. Absolutely nice. But of course, there are also XOR key parts, which were zeros probably. So let's just run our generator. And let it work. Okay, we are getting this key fully synthesized now. In some seconds, it will be finished. And of course, I will show you the full file structure of this case. Okay. And of course, we can now just delete the connection from the offset and add it to the whole chip. Markers table was prepared previously, and here we are getting the full structure. all the files are working because ECC was corrected also. The dump looked pretty good, and here are our files. Okay, so let's move on to the next case. The main case, I think, today, because we will talk about FC controllers and two features. As I said previously at the start of our presentation, we have introduced the SLC read modes, and here you can clearly see that only SLC blocks are used. And if we are talking about dump, here is its image. And you can see that data was written only in pseudo-slc mode. And unfortunately, we needed to read this chip manually with our old configuration without using our new reading mode, because we received this chip some time ago, and it's not more available in our lab. Unfortunately, one of our partners was able to collect it back. But if we look here in this offset, we can see that data is extracted by a similar offset. It's quite regular, so we didn't need to build an arranger and markers table. We were not using page filter as it usually was in the past when we were working with pseudo-slc devices. Okay, and now you can surely you can read such chips in the SLC mode from the very beginning and work with data, not extracting the SLC pages from the MLC blocks. So the data will just look like this from the very beginning in this section, just after reader. Okay, so let's move on to our bit column remover. I would like to tell you that in this case, there were bit columns only in one plane, and I will now show you the positions of these bits. Let's move on to the data. Of course, I would like also to tell you that we have precised the page structure previously, and in this case, we have 1024 bytes of data, and then 3 bytes of assay, and then 120 bytes of ECC. So let's move on to our bits. And of course, I will also show you there's a problem with bits added to the end of each code word. Here, you can see that we have removed some bits from our byte. It's clearly seen that there are good bits like this two, this one, and this one in these 2 bytes, and we will need them to work properly with our data. And of course, to correct our dump, to make ECC, and to get the file structure, of course. And in this case, some disclaimer that file structure also will be shown. Okay, so as you can see, if we move on to our next BUT bits, there are two BUT bits at one moment. And as you can see, there are only two cases in this dump when we have only one BUT bit, and they are not going sequentially. Usually there are groups of two BUT bits in one byte. Okay, so you can see that here we have 3 BUT bits, and then 2 BUT bits, then 4 BUT bits, and then again 2 BUT bits within 2 bytes. And then if we will go to the end of this code word, we can see that there are 5 BUT bits removed also because that's the end of our code word. And as I said previously, we should remove those BUT bits that controller return to the end of the code word to make the next code word start from the proper byte, from the proper position. And you can see here that those 5 bits are looking like some garbage. That's something you can see in while removing bad bytes columns. So we can just delete them, and then our next code word with data will start from the proper position, and we will not have problems with data extraction then. Okay, so let's move on to our next BUT bits. They are located. Okay, I have a questions. Code word means page. No, if we are talking about code word, we mean the part of the page that includes one data area chunk, one service area chunk, and one ECC. Usually we have a deal with 8 or 16 code words. It depends on the page size. So if you have 16 kilobytes a page, then we are talking about 16 code words. 8 kilobytes page, then 8 code words, and I think that's clear. Here in this code word, we had 2 BUT bits. They were laying quite nearly each other, but in the different bytes, so we can just delete them and then move on to the end of our code word. And here we had an interesting situation when the controller had written 6 additional bits, and then the controller had made a copy of the last byte of the code word, the whole byte, and we can just remove this garbage byte too. You can make it here or using standard BUT column remover, but we have made it in this element, just removing 8 bits and making it the whole byte. As you can see here, looking at this pattern, it's clearly seen that this byte is copied here, and we should remove this, the whole byte, to work with our structure. Okay, can BUT bits be XOR too? At the moment, we had not met a situation when BUT bits were XORed. They are clearly seen in a dump. They are looking like BUT columns, but just in bits. Okay, so if we are talking about BUT bits, let's conclude about the end of the code word. As you can see here, these positions that I'm showing at the moment, they are related to one code word. They are located near each other. And if we will calculate them, if we will add these positions, we will receive the number equal to 11, which means that controller had reserved 2 whole bytes to these bud bits, and here are positions of our bud bits, and here we have deleted 5 additional bits from the end of the code word to make the next code word starting from the proper place. Totally, in this code word, we have 16 deleted bud bits, which means we have deleted 2 whole bytes. And here we have similar situations, but for some reason, controller have also written additional byte to the end of the code word, but we have also deleted it, and we got good looking page structure. Okay, so I think we can move on to ECC, which was detected automatically. If you can see here, let me show you that here we have extracted blocks with data in this markers table, and then we can just create the image and have a look on this. I will be honest with you, in this case, previously we were extracting XOR key using Arranger, and as I said, in this case there were not a lot blocks with data, so we have just extracted the blocks with data and run the XOR key generated on it, and let me show you that just works. We can find here element block arranger, and here, if we will run our element, that just works. Okay, and that's synthesized, and I guess that this element and this element will be equal, so there is not a big sense to reconnect the elements. And we have a data. Okay, so let's finish. Thank you very much for attendance, for your patience, and see you all. Goodbye.